nasa.gov/messenger. Let me introduce you to today's participants. First up, Brett W. DeNevy, scientist, Johns Hopkins University Applied Physics Laboratory, otherwise known as APL, in Lowell, Maryland. Larry R. Nittler, scientist, Department of Terrestrial Magnetism, Carnegie Institution of Washington. Sean C. Solomon, messenger, principal investigator from the Carnegie Institution also. And Ralph L. McNutt, Jr., messenger, project scientist, also from APL. Before we start with the official presentations, it's my honor and privilege to turn over to Sean for some opening remarks. Sean?
Thank you, Dwayne. We're delighted to be here today to share some of the findings from the first 25% of our year-long mission, Messenger, in orbit around one of our nearest planetary neighbors, yet a planet that has never had an orbiting spacecraft before Messenger. I wanted to begin by telling you that we passed some substantial milestones just earlier this week in our mission. On Sunday, we had the first perihelion passage, closest approach to the sun since we've been in orbit. On Monday, we logged in 1 Mercury year in orbit. On Tuesday, we came out of a solar conjunction when the sun was in between Earth and the spacecraft, allowing us to communicate again after being blocked. And just yesterday, we had the first orbit correction maneuver in orbit that lowered our closest approach to the planet back down to 200 kilometers or 120 miles. On most days since we've been in orbit, we have received new data about this planetary neighbor of ours almost nonstop. New images, new data from all of our 7 instruments. We had many ideas about Mercury that were incomplete, ill-formed, that came out of the few flybys, the 3 flybys by Messenger and the 3 flybys in the 1970s by the first spacecraft to visit Mercury, Mariner 10. Many of those ideas are now having to be cast aside as we see orbital data for the first time. We are confirming a few of the theories that have preceded us, but many of those theories are now being cast into the dustbin of science as they are shown to be a very incomplete or incorrect description of the innermost planet. You'll hear examples of those from each of the presenters today. One of our instruments on the spacecraft is, of course, our imaging system. We've taken more than 20,000 images of Mercury to date, and I'd like to turn the microphone over to my colleague, Brett DeNevy, who will describe some of the things we're learning from those images. Brett?
Thank you, Sean. Well, it's my privilege today to share some of our early science results from the orbital imaging campaign. If we can pull up the first image. This is a view of Mercury looking down on the North Pole. And this is an area that we didn't really have great coverage of before due to the nature of flybys. So you can see on the left half there, it's mostly all of our new orbital coverage, where we filled in pretty much all of the gaps consistently. On the right-hand side, we haven't yet marched all the way around the planet to fill that in, so it's still showing some of our flyby coverage. But what you can see there in yellow outlined is the approximate extent of a really large unit of smooth plains. And these plains are thought to be volcanic in origin. And we had some hints from the flybys. Mariner 10 actually got the best look of these plains, but now we're seeing for the first time their full extent, which is around 4 million square kilometers. It's around half the size of the continental U.S. And if we can go to the next graphic, you can see this is just an example of how we actually did see some of these planes during the flybys, but because we're flying by close to the equator, looking up at high latitudes is really a difficult challenge, and so orbit is perfect for that. If you can add the overlay there, you'll see this is the same area as seen from our flyby images, where we can look straight down on the surface. And so from our more detailed look at this beautiful large unit of smooth plains, we're seeing all kinds of evidence for volcanism, the tectonic deformation of these plains. In this image toward the center and on the right side there, actually you can see ghost craters, which are pre-existing impact craters that were later covered over by lava. And you can just see their rims affecting the structures there. If you can bring up the next image, please. We're also orbiting, in our orbital coverage, we're collecting color images through 8 color filters of the whole planet with a resolution of around 1 kilometer per pixel. And so the reason we image Mercury in color is so that we can try to understand its composition. The colors of the surfaces are related to the rock types that are present on the surface. And so this image is also showing the smooth plains. They're the less cratered area that shows up as kind of an orange or red in this color scheme. If you bring up the next image, or the last image, sorry, was an image where the infrared red and blue filters were in the red, green, and blue channels. This image is an enhanced color look at the same region. That just shows these smooth plains are compositionally distinct from their surroundings, and while we don't yet know their composition, that's something we're working on. But we're really excited to keep studying this huge volcanic deposit near the North Pole, its implications for the evolution of Mercury's crust and how it formed. Next slide, please. This is just showing our coverage so far that we've obtained from orbit in our monochrome mapping campaign. So you can see in just around 3 months, less than 3 months, we've filled in a great deal of the planet already, at least for this hemisphere. If you can start the movie, when we zoom in here, you can see this images are collected at an average resolution of around 250 meters per pixel. And when you zoom into the full resolution, you can start to see this is just one of the many spectacular features on Mercury. This is a 13-kilometer impact crater, and that dark region that you see to the south is impact melt, which flowed from the crater. Impact melt forms when the impact occurs. The temperatures and pressures are very high. They melt the rock on the surface, and it can flow, in this case, away from the crater. And this particular view here shows the impact melt is very dark. The color imaging and also the reflectance spectrometer on MESSENGER hint that this may be a unique composition, distinct from its surroundings, and definitely different from most of the typical impact melts that we see on Mercury. Next, please. In addition to our standard color and monochrome mapping imaging campaigns, we also are able to collect high-resolution targeted images for regions that are of high scientific interest, things that we saw during the flybys and wanted to get a better look. This is showing the crater Degas, which is around 50 kilometers in diameter. On the left-hand side, you'll see that was the coverage from Mariner 10. And so our targeted images and color here are acquiring a great new level of detail. You can see on this crater there's impact melt that covers the floor. It has these fractures that formed as the impact melt cooled and solidified and cracked. And then the beautiful bright area in the center is the central peak complex there. And the next slide, please. We're also able to acquire targeted monochrome images, and this is a great example of the importance of these high-resolution images. MESSENGER can acquire images at up to 10 meters per pixel. This one here is 21 meters per pixel. And it shows a region that we saw these areas during the flybys that had patchy, bright material on crater floors, sometimes in peak rings of craters, and we simply didn't have the ability to determine what they were because we couldn't see it at any higher resolution. We look at these targeted images, we can see that these patchy, bright regions are actually terrain that appears to be etched. There are clusters of small, rimless depressions, a few hundred meters to a kilometer. They often have diffuse, bright halos around them. The line in the bottom image where you can see kind of a line of these little pits and etched terrain, that's actually the peak ring of an impact crater. And so we still aren't sure how these formed. There are a couple ideas. When you see rimless depressions like this, in other places they're often due to an explosive volcanic eruption where you have a gas that when it gets near the surface and the magma expands, explodes, like Mount St. Helens, for example. But these features do appear quite different from the typical vents that we see on the moon or on Mercury. They're really unlike anything we've seen before. So another idea is that they contain some kind of material or compound that is not stable when it's exposed near the surface of Mercury. So a volatile material that evaporates or sublimes when exposed at the surface. So we're really excited to keep studying these features, try and understand their origin, apply data from all of the other instruments on MESSENGER. And with that, I'll pass to Larry.
Thank you, Brett. I'm very happy to be here today. I'm going to talk about results we've gotten from two specific instruments on MESSENGER, the X-ray spectrometer and the gamma-ray and neutron spectrometer. These instruments are designed to measure the abundances of the chemical elements at the surface of Mercury. Now, the abundances of elements on planets depends on what the planets were originally made out of, their entire geological history. So they're very diagnostic of important processes. Over the years, many ideas and models have been put forward about what the composition of Mercury might be based on various formation models and evolution models. But it was only until now that MESSENGER is in orbit around the planet that we can actually start testing these models in detail and really see if any of them are right. And what we were finding, as Sean indicated, is that in many cases, a lot of the original ideas about Mercury are just plain wrong. And so we're finding some surprises, and we're getting very interesting results, as I'll show you. So this first animation is an illustration of how one of these instruments works, the X-ray spectrometer. Now, we use this instrument. Basically, X-rays from the sun are emitted by high-temperature plasma in the outer atmosphere of the sun. These X-rays hit the planet, and they can cause re-emission of fluorescent X-rays. This is very much like a black light poster glowing under a UV lamp. So it's a fluorescent process. These X-rays can be detected by the instrument on board the spacecraft and used to determine what elements are present and in what abundance. So this technique depends, as I said, on the X-rays from the sun. The solar X-ray emission varies with time wildly and gets especially high during large solar flares. Well, we've been fortunate that the sun has been relatively active since we went into orbit 3 months ago. So we've gotten some very good fluorescent X-ray data from the surface. So we're getting good measurements right now of the average composition of key elements like magnesium, aluminum, silicon, sulfur, calcium, titanium, and iron with this instrument. So as an example, may I have the next slide, please? This shows a graph of the magnesium to silicon ratio plotted against the aluminum to silicon ratio for different types of rocks on the Earth and on the Moon and on Mars. And what you can see is that these different types of rocks and planets lie in different places on this plot. And so it's a good discriminant of different processes. For example, at the bottom right, you can see that rocks from the interior of the Earth are relatively enriched in magnesium and depleted in aluminum, compared to typical rocks on the surface of the Earth, like basalts, that can be seen at the sort of middle left with higher aluminum and lower magnesium. Many, many rocks on the surface of the Moon are even more enriched in aluminum than typical Earth rocks, so they're up in the upper left portion of this diagram. And that reflects a very high abundance of minerals, feldspar minerals. So if we go, and on this graph, we can also see that Mars occupies an entirely different region on this plot. So different planets lie in different regions, and where does Mercury lie? Well, if I have the next slide, this shows our data that we're determining from the X-ray spectrometer. The lighter symbols indicate measurements over very large areas, sort of 1 to 2,000 kilometer footprint size, whereas the darker symbols are slightly better resolved measurements down to a few hundred kilometers. And what's clear here is that Mercury is not the Moon and it's not the Earth. The surface of Mercury occupies a fairly unique location on this diagram for the surfaces of terrestrial planets. It's got lower aluminum and more magnesium relative to silicon, so it has a lower abundance of feldspar, and it clearly has undergone a unique geological history. In addition to these data, the X-ray spectrometer has made two additional very interesting observations. First, we have found that the surface of Mercury has relatively low abundances of iron and titanium. Now, it's been known for many years from ground-based spectral observations of Mercury that the silicate minerals at the surface of the planet are low in iron and titanium. But data from the flybys of MESSENGER of Mercury suggested that there, in fact, could be much higher abundances of iron and titanium at the surface that just were not in silicates, were in other phases. Well, the X-ray data clearly showed this is not the case, that the rocky part of the planet is low in iron and titanium. So it helps show the power of orbital missions versus flybys, that even when you get excellent data on flybys, it's not always easy to unambiguously interpret it. So here in the orbit, we're getting this. And again, it shows that Mercury is different from the other planets, which have much more iron and titanium in their rocky portions. The other very interesting observation that we've found is that the data reveal that the surface of Mercury has a very high, relatively high sulfur abundance, on the order of a few percent by weight of the surface of Mercury appears to be sulfur, which is at least a factor of 10 times higher than the crust of the Earth or the Moon. We do not fully understand this yet, but it almost certainly relates to the origin of Mercury, that Mercury most likely formed from building blocks that were fundamentally chemically different from those that formed the Earth and Moon originally. It also has important implications for understanding volcanism. As Brett was talking about, we have evidence for explosive volcanism possibly driven by volatile gases. And on the Earth, this is often driven by sulfur-bearing volatile gases. And so the presence of sulfur should tell us new things about the nature of volcanism on Mercury. So shifting gears, I have the next animation, please. So this is an illustration of the other instrument, the gamma ray and neutron spectrometer, which probes material to depths of a few hundred or a few tens of centimeters, a few feet. And basically this instrument works when galactic cosmic rays streaming through space interact with the surface. They make neutrons. They can be fast, high energy, or slow, and then they can get slowed down to be thermal neutrons. These neutrons can interact with materials at the surface to produce gamma rays that have energies characteristic of the elements. And in addition, if you have naturally radioactive elements like potassium, thorium, and uranium, they can decay naturally and release gamma rays. And all of these neutrons and gamma rays can be detected by the instrument on board the spacecraft and used to determine the composition of the planet. I'm going to focus today on the results for potassium and thorium, both of which have radioactive isotopes, so we can detect their abundances. May I have the next slide, please? So the ratio of potassium to thorium has long been understood to be a very useful probe in planetary science. And the reason for this is potassium is a rather volatile element. So it evaporates at relatively low temperature, and thorium does not. So the ratio of these two elements can provide a great deal of information about thermal heating processes that occurred in the early solar system when these planets were coming together. So this plot shows the potassium to thorium for Venus, the Earth and Moon system, and Mars. And a striking thing on here is that the Moon has a much lower ratio of potassium to thorium than the other planets. And this is a direct reflection of the very, very high temperatures that the Moon experienced when it formed by a giant impact of a Mars-sized impactor on the Earth. And it got so hot that the potassium and other volatile elements like it essentially evaporated away. Well, prior to MESSENGER, many ideas about Mercury suggested that it should also have a low potassium to thorium ratio. Mercury formed very close to the sun in the early solar system. It was thought that the nebula from which the disk from which the solar system formed, the planets formed, was hot there. And there are many formation models for Mercury that suggested this ratio should be low. But in fact, the gamma ray results show the opposite. May I have the next slide, please? They've been able to measure this ratio on Mercury, and surprisingly, it's not low. It's, in fact, as high or higher than that of the other terrestrial planets. So this tells us right away that Mercury is not highly depleted in these kinds of volatile elements, unlike previous ideas. It rules out some formation models, and it's completely consistent with other observations, like the high abundance of sulfur, which is also a relatively volatile element, and the presence of sodium, which has been observed over the years in the exosphere around Mercury, and it's clearly been coming from the surface. So there seem to be a large amount of volatile elements in the planet. And all taken all together, these elements are changing our view of the origin of Mercury. It indicates that Mercury is not the Earth, it is not the Moon, and we're going to use these data in conjunction with all the other observations to really try and better understand how the planet formed, what it formed from, and what has happened to it in the intermediate 4.5 billion years. And with that, I will pass it on to Sean.
Thank you, Larry. I'd like to share some of our recent findings from two different investigations from the MESSENGER mission: the measurement of the topography of the surface of Mercury and the measurement of Mercury's internal magnetic field. If we could go to the first animation, you'll see a very schematic depiction of the operation of Mercury's Mercury laser altimeter that sends 8 times a second a short pulse from a powerful laser, and it records the reflection of that laser pulse off the surface. And from the time of flight of the laser signal and from precise knowledge of the position of the spacecraft, it determines a topographic profile underneath the path of the spacecraft. While we're switching to the next animation, let me say that laser altimeter has operated more than 2 million times from orbit so far. And what you see playing out on this animation are tracks color-coded by elevation of the topography of the northern hemisphere of Mercury. We're seeing the broad shape of the planet for the first time. We're seeing detailed profiles of geological features, impact craters and basins, fault scarps, volcanic terrain. You're seeing that the northern region of the planet is surprisingly low. The area of the northern plains that Brett talked about has some quite low but variable elevations, several kilometers below that for the average of the planet. The total range in elevation is as much as 9 kilometers on the basis of observations to date. One of the investigations that we're using altimetry to pursue is a 20-year-old mystery that was set by Earth-based radar observations. And the next graphic shows a modern radar image of a portion of the north polar region of Mercury obtained at the Arecibo Observatory in Puerto Rico. What you see are bright deposits at radar wavelengths that are thought, on the basis of their radar characteristics, this is a 20-year-old proposal, to be water ice, this on the planet closest to the sun. Now, that planet gets very hot at the equator in the daytime. So how can there be water ice at the poles of Mercury? The hypothesis, now going back 20 years, is that water ice resides on the floors of impact craters that are in permanent shadow, that never see sunlight, and therefore are extraordinarily cold and remain cold for millions or billions of years. Well, we are testing that idea with several of our investigations, but today let me tell you that the first test has been with altimetry. The next slide shows an example of one of these craters on one of our global mosaics. The one circled in red hosts polar deposits on its floors. You see the radar map superimposed on the global mosaic from MESSENGER. And our altimeter made several passes over this particular crater, 25 kilometers in diameter, 15 miles across, early in the orbital phase of our mission. And the next slide shows a contour map of that crater built up by the topographic profiles that we collected from orbit. And this contour map, combined with calculations of where the sun shines as a function of time of year and position on Mercury's surface, allows us to test what parts of the floor of this crater and other craters at high northern latitudes are in permanent shadow. And indeed, this crater passes the test. The portion of the floor that is in permanent shadow coincides with the portion of the floor of the crater where we see the radar bright deposits hypothesized to be water ice. So stay tuned. This is a very exciting hypothesis, now with us for 20 years, that planet Mercury may have large quantities of ices at the North and South Pole. The very first scientific test of that hypothesis using MESSENGER data from orbit has passed with flying colors, and we look forward to results, particularly from our geochemical remote sensing instruments, the neutron spectrometer in particular. Given enough time from orbit, and 1 year we've shown is enough time, so stay tuned, we'll demonstrate whether or not the material at the poles is likely to be water ice on the basis of excess hydrogen. Let me turn now to the magnetic field of Mercury. The magnetic field was discovered by Mariner 10. It's much smaller than the magnetic field of the Earth. You probably know that Venus and Mars do not have a magnetic field, so Mercury is the only other Earth-like planet to have one. And what we thought on the basis of the flybys was that Mercury was a miniature version of Earth's magnetic field, produced by similar processes and with broadly similar geometry. Now that we're in orbit, we can measure that magnetic field every day. And what we're seeing is that it is not a miniature of the Earth's field. Before you start the animation, let me say what you're going to see.